What if I told you that one of the most powerful machines ever built has no engine, no turbine, and no fuel? It moves millions of liters of water using only one invisible force: gravity. Across the dry and unforgiving landscape of Pakistan, an enormous engineered channel cuts through the earth. It crosses scorching plains, seasonal flood routes, roads, bridges, and remote agricultural land. This is the Kachi Canal project, a monumental attempt to carry life from the Indus River system toward the arid regions of Balochistan. And the most incredible part is not simply the size of the canal. It is the precision required to make every drop travel in the right direction. Before we follow the water, take a second to subscribe to the channel. Here, we reveal how the world's greatest engineering projects are designed, constructed, tested, and finally brought to life. The story of this canal begins long before concrete is poured or water is released. Engineers first have to understand the land. Survey teams establish the canal centerline across vast areas of dry alluvial soil. Every elevation is measured. Every change in terrain is studied. The entire route must descend gradually enough for gravity to keep the water moving, but not so steeply that the flow becomes destructive. A small error in elevation could slow the canal, cause sediment to accumulate, or create dangerously fast water. Once the route is locked, construction crews clear the corridor and prepare access roads. Heavy machines begin cutting an enormous trapezoidal canal prism into the earth. Excavators remove layer after layer of soil. Bulldozers shape the banks. Graders refine the slopes. Rollers compact the subgrade until the ground becomes strong and uniform. The geometry is deliberate. A broad, flat canal bed carries the main flow. Sloping banks provide stability. Raised embankments create freeboard, protecting the surrounding land from overtopping. A permanent service road follows the canal, allowing inspection teams and maintenance vehicles to reach critical structures. But earthwork alone is not enough. Water can erode soil, penetrate weak layers, and gradually damage an unprotected channel. That is why the canal receives a carefully constructed concrete lining. Granular bedding is placed over the prepared surface. Guide rails and forms establish the correct thickness. Concrete is poured across the canal bed in controlled strips, followed by panels along the sloping sides. Each section is finished to create a smooth hydraulic surface. Construction and contraction joints divide the lining into manageable panels, allowing the concrete to respond safely to heat and temperature changes. Flexible sealant protects these joints from leakage. Under the intense Pakistani sun, the new concrete must be cured carefully. Only after the lining reaches the required condition are the forms removed and the entire canal prism cleaned. Yet the canal is much more than a long concrete channel. Water must be controlled. At strategic locations, reinforced concrete regulators rise across the canal. Their piers support large vertical steel gates. Powerful hoists, lifting shafts, motors, and gearboxes allow operators to raise or lower each gate with precision. A small change in gate position can alter the water level and discharge throughout the system. Beside the regulator, a control house contains the power, monitoring, and operating equipment. Sensors measure gate positions and water levels. Electrical cables connect the machinery. Earthing and lightning protection safeguard the installation. Technical lighting makes safe operation possible after sunset. The project also has to survive the environment around it. Seasonal hill torrents can suddenly send runoff across the canal route. Instead of allowing floodwater to damage the embankment, engineers build protected cross-drainage structures. Filter layers and heavy riprap resist erosion. Guide banks and flood protection bunds direct the runoff safely. An escape regulator provides another level of control. If the canal level rises too high, operators can release a limited amount of water into a separate escape channel. At the end of that channel, an energy dissipation structure reduces the force of the flow before it reaches the protected outlet. Road bridges cross the canal, connecting both sides of the corridor. Culverts maintain drainage beneath service roads. Parapets protect vehicles, while deck drains remove rainwater from the bridge surface. Then the main canal begins to divide. A branch canal carries part of the flow away from the main channel. From there, water enters a smaller distributary. The distributary feeds a minor canal, and the minor canal supplies a narrow watercourse leading toward the agricultural fields. Each channel is smaller than the one before it. This hierarchy allows engineers to divide and measure water instead of releasing it without control. Turnout structures direct the flow, while measuring sections help operators verify the quantity moving into each part of the network. Before any water is allowed inside, the entire pilot reach must pass a strict dry inspection. Construction debris is removed. Concrete panels are examined. Joints are checked. If inspectors discover a defective section, it is clearly marked, cut out, cleaned, and recast. The repaired area is inspected again. Next come the mechanical tests. The main regulator gates move through controlled dry cycles. The escape gate is tested. The branch gate is tested. Motors, hoists, sensors, backup power, access systems, roads, bridges, and safety equipment are inspected as one connected system. Only after the dry acceptance is complete can the most dramatic stage begin. First, water. One head regulator gate rises only slightly. A thin sheet of water passes beneath the steel gate and moves onto the previously dry concrete lining. The canal is not filled quickly. Engineers deliberately keep the level low so they can inspect every wetted surface. They watch for leakage, unstable joints, seepage, erosion, or unexpected movement. When the lining passes its wet inspection, the main regulator is tested under flow. Water moves through the gate and enters the stilling basin, where the energy of the discharge is controlled. The escape regulator is tested next. A limited release travels through the escape channel and reaches the protected outlet without damaging the banks. Then, the branch gate opens. For the first time, water leaves the main canal and enters the distribution network. It advances through the branch, passes the measuring structure, continues into the distributary, enters the minor canal, and finally reaches the pilot watercourse. The levels are raised slowly until the entire pilot system reaches its initial operating condition. And then comes the moment this entire project was built for. The first field outlet opens. Water flows from the watercourse onto the carefully leveled pilot plot. It spreads across the dry soil in a shallow, controlled sheet. At first, the transformation is subtle. The ground becomes darker. Small, wet areas appear. After continued measured irrigation, the earliest green shoots begin emerging from a landscape that had been dominated by dust, heat, and scarcity. This is not a sudden fantasy in which the entire desert turns green overnight. Real irrigation development takes time. The canal must operate through extreme heat, dusty winds, darkness, light rain, and changing seasonal conditions. Gates require inspection. Sensors require calibration. Hoists need lubrication. Roads and bridges must remain accessible. Drainage structures must be kept clear. Day after day, operators monitor the system. At sunrise, maintenance teams patrol the service road. At midday, the canal continues flowing beneath intense heat shimmer. At sunset, the water reflects the golden sky. At night, technical lights illuminate the regulator while the surrounding plain remains dark. The water never stops, simply because the camera stops watching. That is the true power of this project. It is not only a canal made from soil, concrete, and steel. It is a carefully controlled connection between a great river system and communities living in one of the country's driest regions. Every survey marker, concrete joint, steel gate, bridge, sensor, and drainage structure serves one final purpose: to move water safely to the land that needs it. The Kachi Canal shows us that the most extraordinary engineering is not always about building upward. Sometimes, it is about creating a precise path across the earth and allowing gravity to do the rest. If this journey from empty ground to flowing water amazed you, subscribe to the channel and turn on notifications. We explore the construction secrets behind the world's most ambitious megaprojects, from the first survey line to the moment the entire system comes alive. Thank you for watching, and I will see you in the next engineering story.